Hello everyone, I'm Jean and today I will present on my project of the smart residence system. This project is originally named Connect Asset Tracking that was provided by a company. It was planned to be implemented in library, however, due to the current lockdown situation, the project is switched to be deployed in a room in a residential hall, which is my room, and expected to be usable for nursing room or elderly house. The smart residence system is an area monitoring system based on sensor network and utilizes machine learning techniques to make prediction on sensory data. First of all, the IoT is basically a system of interconnected and interrelated computing devices where they can transfer data over a network. It has been ever growing in recent years. With the proliferation of IoT devices and the device development of AI technologies, smart environmental monitoring and control system is able to be built and may change the way of people's life and work style in the near future, which motivate us to build the smart residence system. In addition, when we study the term of occupancy monitoring, there are a number of problem variations. They are interrelated, but depending on the goal of the application. The most basic goal is to detect whether an area is being occupied or not, which is so-called occupancy detection. Further, it comes with the problem of counting people in a specific area, which is occupancy counting. Next, in advance of counting people, locating the position of people in the area is occupancy tracking. And then there is occupancy event or behavioral recognition, which is recognizing people's activity in the area. And when investigating these problems, the solutions are mainly addressed in three techniques, which are Wi-Fi, camera, and sensor network. The Wi-Fi-based solution utilizes the widely existing available Wi-Fi access point in the building, works along with users' smartphone or other Wi-Fi capable devices. It's more often used for wide area cases like shopping mall or airports. The solution based on camera uses computer vision techniques, which is thus heavily depends on the quality of frames captured by the camera. It's mostly used for counting people within small zones like entrance of a building or a room. For sensor network-based solution, it uses machine learning techniques to make prediction on sensory data, such as lighting, temperature, all the data collected by sensors. It's more applicable for a room-sized monitoring task, which is also applied by our smart residence system. As I mentioned, the smart residence system is initiated from the area monitoring task in nursing home or elderly house. It aims to be a prototype that can be used in those cases. In a nursing home, the staff needs to take care of the patients in the current way. The patients or elderly need to call the nursing staff by themselves when they need help. However, accident might occur and make patients being unconscious or having physical problems to call for help. So the nursing staff needs to know the state of patient, and hence we comes up with a sensor network-based system. They monitoring the area in a non-intrusive way compared to camera. It frees the use of visual information, monitors the state of room and patient's activity, and protect the patient's privacy at the meanwhile, which is more acceptable in the case of living area monitoring. And since the project is deployed in my room, the scope is designed for three areas: the bathroom, bed, and desk, like showed in this picture. That is the layout of my room. And in addition, some of people's activity could be directly recognized by the state of room, while some activities are recognized by sequential state change. For example, for the bed area, the state defined are empty bathroom, sink occupying, toilet occupying, and showering. And activity of taking shower, using toilet, and using sink are directly recognized by the state of shower, toilet, and sink, while the leaving the bathroom activity is recognized by sequential state change from occupying state, which are sink, toilet, and shower, to empty state. For the bed area, The state defined are empty, sitting, and lying. An activity of sitting down on bed is recognized by state change from empty to lying. The lying state is recognized directly by lying state, and sitting up on bed is recognized by state change from lying to sitting, and leaving bed is recognized by sequential state change from occupied state, which are sitting and lying, to empty state. For a desk area, the state defined are only two states, which are empty and occupied, and the activity is simply leaving the desk, which is recognized by occupied state change to empty state. And in order to show both of the state of room and the people's activity, the application UI includes an activity table that recording the activities the resident does, and a status bar indicating the current state of room, along with a display of the current occupying state of the room. Later, I will show the demonstrating videos for both bathroom and bed area. For the application architecture, there are four main components, which are sensor set, database, backend, and frontend. The sensor set collects the sensory data and sends those data to the database. Those data were next fetched by the backend. The backend will process the data and use pre-trained detection models to make prediction on those data and send the result to the frontend to show to the user. For the sensors, we use the combination of environmental sensors and motion sensors. And we use the Firebase real-time database to store sensor data, and Python is used as the backend language, and we use the website platform as the frontend. For sensors, we use a set contains both environmental and motion sensors, where environmental sensor includes one temperature and humidity sensor, one light sensor, and one sound sensor. And motion sensors includes two ultrasonic distancing sensor and one PIR motion sensor. For the temperature and humidity sensor, the humidity index is always given with the temperature index because they are correlated and interactive, measured by a single model integrated sensor. The light sensor gives value in the range from 0 to 1024, where 1024 means very dark area. The PIR sensor gives binary value, where 1 means it detects the movement of a warm object and 0 otherwise. For the sound sensor, it detects the sound waves through its intensity and converting it to electrical signals. It sends the surround ambient sound and gives data in a weighted decibel. The ultrasonic sensor consists an ultrasonic trigger to emit ultrasonic waves and an ultrasonic echo to receive the waves reflected back by any obstacle object. It measures the distance by measuring the time between the emission and reception. And all the sensors are connected and controlled by Node MCU boards. The boards works as a microcontroller unit with Wi-Fi support, taking action according to the code programmed. In our sensor set, both light sensor and sound sensor needs to use analog pin, but each Node MCU board only have one analog pin. Also, the number of usable pins on Node MCU board are very limited. Thus, we use two Node MCU board to control the whole sensor set. Moreover, each sensor only costs around 30 to 50 baht, and one Node MCU only costs around 100 to 150 baht. The whole sensor set costs no more than 500 baht, which is much cheaper than the camera. And in the real implementation, we actually use two Node MCU. Thus, there are actually three parties needs to access the database. And meanwhile, the sensor collects the data in milliseconds level. However, updating the data to database in millisecond level could cause database resource competition or database congestion. The data updating speed of Node MCU is within 1 second, around 100 milliseconds. Hence, the updating time of the two Node MCU could be set within 1 second differences. The data downloading speed of the application backend is slightly longer, but still falls in the range of 1 second. Hence, the length of the database accessing interval for both two Node MCU boards and the application backend which is also the interval to make prediction for backend, could be minimized to 1.5 seconds, which could be a bit risky, and 2 seconds should be safe enough. 3 seconds would be absolutely robust and stable for the system. And moreover, the problem of noisy data and missed prediction is unavoidable under any situation. If every prediction is counted and showed to the user, that could cause confusion. Thus, we added a state log to improve the performance. It's like a first in, first out stack that works like moving windows. For example, showed in this picture, if the state B new prediction of state B is a misprediction, instead of showing it directly, we put it into the state log. Then the log counts the number of the represents of each state exist inside, where state A has 4 counts and state B has only 1 count. It returns the prediction result that has the most counts, which is state A. It keeps recording the most recent prediction and dump the first in one. Gives more reliable, stable prediction, which is also more reliable. However, the state log, along with the database assessing interval set, as we said before, it will cause a certain degree of delay, around 10 or more seconds, as the correct new prediction needs to wait until it has more counts than the old one. Nevertheless, the delay is more acceptable than and preferred than unreliable information that could confuse the user. Moreover, before the real implementation of the system, the detection model have to be trained in advance, as I've mentioned in the application architecture, that the model will be used for application backend to make prediction. For the training experiment of models, these are the training result of 4 most representative classifiers, where naive Bayes is for Bayes family, and random forest for tree classifiers, MLP for neural networks, and SVM for which has been widely used. The results for each time of training all have slight differences but similar and follow the same pattern. For the bathroom case, the random forest always gives the highest accuracy of around 99% and followed by MLP of 97%. And among all the classes, the shower class always have the lowest recall, and all the classifiers tends to recognize sink state as shower state. For the bed case, the MLP often gives the highest accuracy, around 94%, and among all the 3 classes, lying class gets the highest F1 score in most of the time, while empty state and sitting state often recognized as each other. For the desk case, all the classifiers could get high accuracy, also bad accurate score at the same sometimes. But since there were only 2 classes, all the classifiers usually yield a high accuracy score over 90%. However, because the training sample of occupied class is less than empty class, classifiers tend to classify occupied state as empty state. Overall the cases, the MLP performs the best and is also used by our system. Next, I will show the demonstrating videos for the bathroom and bed area. This is the demonstrating video for the bathroom area for the state of empty sink and toilet. For now, you can see the status of bathroom is empty, and then I go and sit on the toilet. After the front end receives the reliable detection, the activity of using toilet is recorded on the table, and the state bar changed to toilet is being used. And the logo of the toilet is also lighted up. And same goes with the sink using the logo of the sink is lighted up, and the activity and the status were indicated respectively. And after I left the bathroom, the notification of the resident has left the bathroom is showed up, and the activity and status are recorded and showed as well. For the shower case, I show the application UI along with the temperature and humidity index change. You can see that the activity and status of shower is showing on the UI, and the temperature and humidity is keeps increasing during the shower. And usually the humidity will keeps increasing and stop by 95%, the maximum humidity relative humidity index the sensor can measure. And for the bed area, the bed is empty now. Then I go and sit on the bed. The activity of sitting down on bed is recorded and the state is indicated. And then I lie on the bed. The activity on the state were showed at the same time. And after next, I sit up on the bed. The activity was showed as sitting up, different with the sitting down activity, but the status of these two activities were the same, which is sitting on the bed. And after I left the bed area, the notification of leaving the area is showed up. And that's the demonstrating videos. Um, And overall, as showed in the demonstrating videos, the sensor network-based area monitoring system that utilizes machine learning techniques is possible to build and capable to be the proof of concept prototype system for nursing home or elderly house. And due to the aging population problem, we believe this kind of system would be much helpful and useful in those cases. And that's all for the presentation. Thank you.